These selective ion channels are very important because they selectively allow ions to flow down their concentration gradients. These are the most basic of the ion channels. We call them leakage channels because they passively allow certain ions to pass through. In a real neuron, we have a lot of passive potassium selective channels and fewer passive sodium and chloride channels. Because the potassium permeability is much higher than the other channels, potassium dominates the resting potential. But any ion that can pass through the membrane, even a little bit, will contribute to the overall membrane potential. If you're particularly astute, you'll realize that we left one loose end. Earlier, we showed you how having a significant permeability to sodium would cause the resting potential to unravel, because in that scenario, both potassium and sodium can travel down their concentration gradients without ever developing an electrical gradient. This is like having a separate door that lets the Americans get into the inside room. The sailors mix, and the gender imbalance never gets out of hand. It's sort of like an exchange program. As long as we trade British and American sailors 1 for 1, we can keep the gender ratios in order. As we've seen, that's not the reality of the situation. British sailors, that is potassium, can move easily, while American sailors have a hard time getting through. But it's not impossible. Imagine a world where every so often an American is able to sneak through. Once he's on the other side, he's rather happy. He's fulfilled his mission to equally cover the territories, that is, he's diffused down his concentration gradient, and the gender ratio is better here, that is, he's also moved down the electrical gradient. Give an inch, take a mile. It won't happen immediately, but given enough time, eventually enough Americans will find their way into the inside room, and the whole system will be at equilibrium. We can't have that. We need to take action to keep things in order. In nature, the solution to maintaining this electrical gradient is the sodium-potassium pump, which continually moves 3 sodium ions out of the cell for every 2 potassium ions it pumps into the cell. This powerhouse uses ATP, a key energy-carrying molecule in biology, to drive its function and maintain an electrical gradient in neurons. The transport of sodium out of the cell and potassium into the cell is so important to neuronal function that it consumes up to 70% of the ATP required for overall brain function. That's a lot of energy just to maintain an electrical gradient. To put that in perspective, something like 1/3 of everything you eat in a day goes to powering this pump.